Hello! In this video we're going to go through the part 1 of section 11.1, which is over limits. Let's dive right into calculus. So we're going to see an example. We want to start off and we want to know the value of x equals 2 for x squared minus 4. So let's go ahead and graph this. It's a parabola, it's a graph we've seen several times before. When x is 0, we're down here at negative 4. When x is 1 squared minus 4 is negative 3. When x is 2 squared is 4 minus 4 is 0. And when x is 3 squared is 9 minus 4 is 5. So over here at 3 we're at 5. And then 4 squared is 16 minus 4 is 12. That's kind of off our grid. It's a parabola, so we actually do have the symmetry with the graph. At negative 1, we're still at negative 3. At negative 2, we're still at 0. And then at negative 3, we're still up here at 5. And you can plug those values in to see that. So that's what our graph looks like. Again, it's going to go off the map. I don't really care how accurate this graph is, but there's our parabola. Again, we wanted to know what happens at x equals 2, so from a pure let's figure out the answer standpoint, we could have just plugged this in. F of 2 is 2 squared minus 4. That's 4 minus 4, that's 0. So therefore, you'll see these 3 dots mean therefore, if you haven't seen that before. Okay. Therefore, f of 2 equals 0. The reason I'm bringing in the graph, because we could have done this part without the graph. The reason I'm bringing in the graph is I want you to see what the function looks like it's doing. As x gets closer and closer to 2, what's happening to the graph? Well, our graph is going down. At x equals 0, it's 4. As we get closer and closer to 2, your function is going to 0. Which brings us to our first definition. Let f of x be a function and let a and l be real numbers, such that f of x is defined for all x around, but not necessarily including the value of a. If, as x approaches the value of a, we have that f of x approaches the value of l, then the limit of the function as x approaches a is L. I know that's a mouthful, and it's not as scary as it looks. It's just a lot to say. If we want to write down in math notation everything we just said, we're going to write the limit as x gets closer to a of this function f of x is L. Okay? Now, with our business calculus textbook, there are some limits methods that the book goes through that we're not going to bother with, and that's more going through and find calculator approximations. What happens when we plug in 1.9 or 1.99 or 1.999? We're not doing that because we don't need to worry about that. What I really care about is this. I'm going to write it down above example 2. What does the function look like it's doing? That's the question, especially if we're looking at the graph, that you want to ask yourself. What does the function look like it's doing? Notice how in our definition we say we want f of x defined around a. We want it to be defined around a. But we don't really even care what happens at a. We just want to know, what does this thing look like it's doing? So, going back to our first graph, as x gets closer and closer to 2, your graph is coming up and approaching 0. And that's the limit. You go to the other side as we get closer and closer to x equals 2 from the right, going from 5 to 4 to 3. Your graph is dropping down to 0. So So that's what it looks like it's doing, and for almost every function that you studied in your life, that's what it has been doing anyway. So let's get into the fun stuff. Okay. Example 2, we want to evaluate the following limits. Again, the most important thing with limits, graphically speaking, is what does it look like it's doing? So for part A, we want the limit as x goes to 4. Again, we have our x-axis right here, so we're just looking one-dimensional on this number line. As we get closer and closer to 4, what does our graph look like it's doing? Our graph looks like it's going to 4. And since it's nice and clean and in front of us, that's our answer. It's going to 4. When x is 4, y happens to be 4. Easy peasy. As x approaches 3, here, okay, what does our graph look like it's doing? This is a more difficult question to answer, because as we approach 3 from the left, as we go 1, 2, 3, our graph is going down. And in fact, it's going down to a negative infinity. It's like going down fast. But if we go to 3 from the other side, from 5 to 4 to 3, now our function's going up. And that's a problem, because what does it look like our graph is doing? It looks like our graph is going 2 different directions. We can't have that. So as x is getting closer to 3, our function can't make up its mind. And this is going to be the answer sometimes. The limit does not exist. Now, if you're kind of writing this out, you can say that, just D and E does not exist. You can say, hey, it's undefined, because both of those are true. Your graph doesn't look like it's doing any one thing. It looks like it's doing 2 different things, and we can't have that. So sometimes the answer is going to be, hey, this doesn't exist, it's undefined. Let's look at another one. So making sure we have what I want. Okay. We have a new graph. It's g of x this time. That's okay. As x approaches 1, as x gets closer to 1, let's see what our graph is doing. So here our graph, as x gets to this 1, looks like it's going to 6. Now, we might want to be a little bit careful, because you can see this hole here. If I were to ask you what g of 1 is, g of 1 is undefined, because there's a hole there. We're close to 1, there's values. We have the line going up, we have the line going down. But when x is 1, this function's undefined. When it comes to limits, that doesn't matter, because our goal is, what does the function look like it's doing? What does the function look like it's doing? So as x approaches 1, our function looks like it wants to go to 6 on both directions. Going up to 6, coming from the other side, it's coming down from 6, and that's the answer. I don't care if it's defined. I don't care if g of 1's defined there. We have a pattern. We know what our function looks like it's doing. For x equals 5, this one's nicer, okay? Because when x equals 5 here, we have a clear-cut answer. When x equals 5, our function is defined and is going to -6. The last thing we're going to do in this video is kind of look through the limit rules, and then we're going to get all the algebraic practice in the second part of this lesson, which is day 2. But let's go ahead and look at the limit rules. With the limit rules, I'm not really going to ask us to know these and use these and go through these step by step. If you ever end up taking calculus, where you have like the trig, in inside of it as well, like regular calculus as opposed to business calculus, then you probably will go through these a little bit more step by step. But I really just want us to be able to see these. Okay? Let A, R, cap B be real numbers, and let f and g be functions such that as x approaches a of f of x, we get A, and as x approaches a of g of x, we get b. So we have functions go into a value, their limits exist. Okay? If you have a constant function, that limit's just going to be that constant. Piece of cake. For the function just x, as x approaches a of x, you're just going to get that value of a because you have that diagonal line. So here you would just have, hey, if that's a, then that also has to be a because we have y equals x. So they're the same thing. This third one's the nice one, okay? If you have this limit and that limit and you're trying to add those two functions, then it is actually just the sum of the limits. It works out very nicely for us. Same thing for the difference. The limit as x approaches a of f of x times the limit as x approaches a of g of x. Again, the product is the product of the limits. Okay. Same thing for the quotient. As long as that denominator is not 0, you're okay. And then we can even raise this to a power and say, hey, if we have this limit that exists and we raise it to a power, it is just the limit to the power as long as that exists. So again, you can't take the square root of -1. That doesn't exist because we're not working with complex numbers this semester. Number 7. Really, again, I'm not going to have us go through and dive into these rules. I'm not going to have us go through these rules piece by piece in examples because we have much bigger and quicker things to get to. So this number 7 is basically taking all of these rules together and putting it to this. If you have a polynomial and you want to know that limit, just plug it in. Just evaluate that, and you're going to get your answer, which brings us to this. This is the thing that I want you focused on, and this is going to be the main focus of our second half of our lesson next time. As Rule 7 suggests, your first step in evaluating the limit is to plug it in and see what happens. Okay? Just plug it in, see what happens. Okay? As long as you don't get 0 over 0 or infinity over infinity, you're going to have your answer. Okay, so I'm going to just introduce a quick example here on our notes. You can write this down if you want to, but we'll also see more of this in part 2. So example, suppose I want the limit as x approaches 4 of x squared plus 3 over x minus 4. Okay. What this note is telling you is if you want to evaluate this limit, just plug it in first and see what happens. So here, we're going to have 4 squared plus 3 over 4 minus 4. 4 squared is 16, so that's 16 plus 3 over 4 minus 4. 16 plus 3 is 19, and 4 minus 4 is 0. Again, as long as you don't get 0 over 0 or infinity over infinity, you're going to be fine. You have your answer. We can't divide into 0. And because we can't divide into 0, this does not exist. I used it earlier. I'm bringing it back. Therefore, the limit as x approaches 4 of x squared plus 3 over x minus 4 does not exist because we got something divided by 0 and that something wasn't 0, so there you go. Okay, so again, the last piece of this lesson is, in general, your first step is just plug it in and see what happens. If it comes to something you can evaluate, there's your answer. And if you get one of these two, 0 over 0 or infinity over infinity, then we have more steps to do. And that's going to be what we see in the second part of our notes and then into the next section as well. So we're going to stop here, and I'll see you next time.